ready? Okay. So welcome to session. We have two sessions in this lightning talk. We have 1.1, the atmosphere and its dynamics, and then later after the 1.1, we'll have 1.3, the oceans and its properties. Some housekeeping. Please, if you're presenting a lightning poster, line up and talk to the helpers and find where you need to stand. One side note, we have the screen down here so you can see your poster down here so you don't have to turn around and look like this. So just kind of look around here. And then afterwards, I think it starts at noon or 12 o'clock, we can move over to the next room and find your poster, and there'll be an hour-long poster session. So let's kick it off, and thank you. Good luck.
Good morning. My name is Golikova Yelena. My colleagues and I from the Institute of Atmospheric Physics in Russia present this poster. This work is about theoretical and experimental studies of the fine-scale light structure of the middle atmosphere using the acoustic method. I'm going to tell you about a new method of processing infrasound signals is proposed based on their decomposition into individual pulses using the pattern recognition method. If you want to find out more, please come to my poster. Thank you.
Good morning. Yeah, it's not updated version of the lightning talk slide, but yeah, anyways. I'm Peter Akimov. You see my name on the second place here. I'm the radionuclide operations officer in the IDC CTBTO. The work was prepared in the scope of the mentoring program by my mentee, who unfortunately couldn't get visa to come here. That's why I'm replacing her, let's say. The work is about the impact of the natural events, the weather events well known as the dust storms and so on the sampling capabilities of the IMS radionuclide stations. We looked into the data throughout the flow rate, which is reduced in effect of those events. There is a data set of 5 years, I think, not that much comparing to 25 years of other afters. We used actively the information from the ECMWF side, of course, ATM from the PTS, and the state of health data from the IMS sampling. Yeah, you are welcome to chat about this. The session will be 12, right next door, slightly overlapping with the lunch break. But anyways, we're happy to see you there. Thank you so much. Have a nice day.
I present another work together with colleagues from Institute in Kaliningrad in Russia, the influence of acoustic and internal gravity waves from atmospheric storms on the parameters of the upper atmosphere. Our presentation is about a new approach to account for acoustic and internal gravity waves generated by a tropospheric meteorological source in a large-scale model. Please come to this poster to discuss a new approach and results. Thank you.
Morning, everybody. My name is Kwasi Benjamin from Côte d'Ivoire. My poster is about the improvement of IS-17, the Côte d'Ivoire infrasound station detection. The main goal of our poster is to upgrade the IS-17 station by adding additional sensor. This is part of CTBTO in medium-term objectives. The used method is to add 50 assurance sensor to the existing real sensor, and also we combine coherence, SNR, and network covering methods to take part of the similarity of signal across all stations, and also network sensibility to event detection. As a result of our work, we note that the improvement of the directional coherence expands the coverage and homogenized SNR. The network becomes thus more reliable, sensitive, and robust in the face of noise and atmospheric conditions. I invite everybody here to come to see my pastor and discuss with me in the way to improve this work. Thank you.
Good morning. Yeah, so I'm Samuel Christofferson. I work at the CEA, and our poster is about the effects of gravity waves and upper atmospheric models and infrasound propagation. And so we know that gravity waves have an important impact on background temperatures and winds, and also these create small-scale perturbations, which are important for infrasound propagation. And so what we want to do is we applied a 3D transient gravity wave model, MSGWAM, to the upper atmospheric version of the ICON numerical weather prediction model, and compared these, used this to predict infrasound locations and waveform analysis, and found that by including these gravity waves, we were able to improve these infrasound propagation results. So if you're interested in more, come and see my poster at poster board 8. Thank you.
I'm Monica Krista. I am Atmospheric Sciences Officer at the International Data Center of CTBTO. For each radionuclide sample collected in the IMS network, we compute atmospheric transport modeling backtracking simulations using 2 instances of meteorological fields. One comes from the European Center for Medium-Range Weather Forecasts, and the other one's from the US National Centers for Environmental Prediction. And a closer inspection made us realize that the geographical regions indicated by the atmospheric transport modeling backtracking simulations driven by the meteorology from the European Center occupy larger geographical spaces than those driven by the US NCEP meteorological fields. So in this poster, we investigate why this might be the case. Thank you.
Hello, my name is Ufus. I'm a student at the University of Oslo, working with Ch4. And the main objective of our poster is to explore how volcanic infrasound can be detected by balloons on Venus. And in that context, we've used the Honga Tonga volcanic eruption on Earth to benchmark propagation modeling against both balloon and IMS data. And then we apply the same models on Venus to investigate its waveguides. And we found that we can predict relative amplitudes between the different stations on Earth. And on Venus, we show the global morphology of infrasound waveguides at balloon altitudes, as well as some evidence that they are able to support long-range propagation. So if this sounds interesting, please come to our poster. It's number 13. Thank you.
Hello, everyone. I'm Ramana Tsuwand from the Institute and the Observatory of Geophysics of Antananarivo in Madagascar. For this poster, predicting rainfall in advance is crucial for sectors such as agriculture, water management, and risk prevention. And the motivation behind this poster is to explore in a first approach the potential relationship between the infrasound measurement and the rainfall variability. Our objective was to determine whether infrasound could serve as an indicator of the upcoming rainfall quantity. In this study, we analyzed infrasound detection, which are separated into 3 frequency bands, and focusing on the dry season preceding the rainy season. The key result of our analysis is that the middle frequency band of infrasound provides the most reliable metrics for rainfall variability. For more details, we invite you to visit our poster. Thank you.
Good morning, everyone. I'm Lestari Naomi Lydia Pandiangan. Me and my colleagues would like to share our poster about tsunami hazard potential along the Flores Backup Truss. Bali, as one of the Indonesian region prone to earthquakes, lies between the southern subduction zone and the northern Flores Backup Truss. To address this, we use the TOS framework with EasyWave to model a worst-case magnitude 7.4 earthquake. From the processing, we obtained that tsunami wave exceeding 3.4 meters could strike the eastern part of the North Bali coast very quickly. What makes those powerful is its real-time simulation capability. This allows rapid tsunami modeling that can directly support early warning decision-making to improve preparedness and community resilience in tsunami-prone regions. If you like to know more, please visit our poster, P1.3 060 board 18. Thank you very much.
I want to thank organizers first. It's a wonderful conference. It's my first S&T conference, and I only knew two people, Mikhail and Bruce, when I came to this conference, but I already made many new friends. So thank you very much. I came from telecom industry, and so I was building submarine cables for more than a dozen of years. And it just happened that telecom equipment with existing cables actually can show you earthquakes. And the first part of my work is when I was lucky to detect first time when you see polarization changes on a submarine cable between Valparaiso and Los Angeles. It is my first conference, so I put 3 published works. The second work is demonstration that you actually can convert cable into 100 sensors, because in the repeaters that are shown here, we actually have optical loops. So we can convert transatlantic cable into 100 sensor arrays. And today, Mikhail from Bell Labs was showing prototype of new instrument. So from first demonstration that is on my poster, it actually moves into prototype, and hopefully it will be on all those 500 plus submarine cable covering 1.5 million kilometers of cable. And the third piece of work on this poster is slow. It's very, very slow events. So what we actually did last year, we were able to see how lava moves from 400-500 kilometers. Yeah, I'm sorry. Come to my poster and I tell you what.
Good day. So my colleague Thiago and I, we frequently get asked what kind of cool or interesting events we get to look at when we check the hydrophone stations. That is also not my poster. Thank you very much. Here's an interesting one. That's the sinking of the Mole Comfort in 2013. It's the single largest loss of shipping containers on record. And we had a look at data from the hydrophone station at Diego Garcia, and our poster outlines how we went about the detection of the signals associated with the braking, with the basically the separation and then the sinking of the 2 parts of the ship in June 2013. And we are also presenting some transmission loss modeling to support that. Thank you.
So, hello everybody. I am coming from the Technical University of Vienna, TU Wien, and my name is Piotr Borejko. So I am going to talk about modeling of in-water explosions for two situations. The first situation is like a shallow water wedge or coastal wedge with a sloping bottom, and this is an in-water explosion, or the second model which you see on the right-hand side. This is the explosion very close to the ocean bottom. And the theoretical approach is exact, and the solution provides a complete record of the time pressure, 3D problem. So we have, for the first model, downslope receivers and cross-slope receivers, very large propagation ranges, and all waveforms or phases of the wave motion are very well modeled, and for very low frequencies and for taking care about the attenuation of the bottom, the last arriving phase dominates. And it has some more interesting implications, and if you know to see these interesting implications, please come to my poster, board 21. Thank you.
Good morning. So my name is Tiago. I'm a hydroacoustic officer at the International Data Center. So the main motivation for this work is from a question from one of CTBTO analysts, Urtnasan, that is also a co-author. So he asked me and Rodrigo, also the second co-author, what could be the main reason for observed high time residuals for T phases in the Pacific Ocean, observed at the station Ch4 and H11. So the time residual is the difference between the observed and the predicted travel time. And in this particular case, the time residuals can go from minus 150 seconds to plus 150 seconds. And this brings a lot of uncertainties when you want to add one detection to an event. So here we have some plots from our analysis. Please feel free to stop by our poster will be there, and we'll try to explain you what is the reason for these high time residuals. Thank you.
Hello, I'm Siobhan Nicholson from Los Alamos National Laboratory in the US. Our poster today is about detecting seismoacoustic events on a hydrophone in the Arctic Ocean. We find that sea ice concentration and other factors control seasonal sound patterns. Here on the top right, you can see the sea ice concentration in the Beaufort Sea at the onset of acoustic summer, and the circle represents the location of our hydrophone. Come see our poster to find out more about how changing environmental and anthropogenic noise impacts hydroacoustic event detection. Thanks.
Hi, I'm Lana Tibulak. I work for the Air Force Technical Application Center, and like in Tiago's case, our analysts came and asked, why do we have 9 minute time residuals for some of the phases that we see in the Sea of Japan? Those T phases were not supposed to be even seen. So if you would like to know why, and also if you would like to know other parameters, other spectral and time domain parameters of the T phases which are related to depth, which we found that are significant, please come by our poster.
So, hello everyone, I'm a PhD candidate at the French National Data Center, and I work on the classification of hydroacoustic data. Our poster presents automated method to classify 6 types of sources. So earthquake, volcanic activities, cryospheric activities, biophonic sounds, air gun, and chemical explosions. We used the data of all hydroacoustic stations from 2020 to 2024, and we present the result obtained in 2024 for the Diego Garcia SUF triplets. Thank you.
Hello. So our e-poster is about a code that we have been developing and improving to simulate 3D transmission losses, which is famously computationally complex, and about enhancements that we've made lately, especially in the context of moving towards higher-end GPUs on the cloud and the lessons learned in that process. So you're invited to approach if you want to know more.
Hello, I'm David Delosto from the Applied Physics Laboratory at the University of Washington. And in my poster, I'm going to cover a number of measurements made over the last 30 years from a fixed acoustic source off of Hawaii. Our colleague, actually, Bruce Howe, intimately knows this source. And it had transmitted during an acoustic thermometry program in the 90s and early 2000s. And then when the IMS came online, we were able to turn this back on in the last 3 years and get some modern measurements of deep ocean temperature. And perhaps what would be interesting to comparisons of what we're seeing in terms of travel time at a station. It's not related to the seasons, but it's more related to climatic events happening with El Nino or La Nina cycles that occur over many years. So we'll see shifts of a few seconds in the, or up to a second over this 3,200-kilometer path. So I didn't put any figures here, so please come by the poster and take a look at some of the data in comparison to physical measurements with the Argo program. Thank you.
Good morning, I'm Ronan Lebras. I'm a former CTBTO employee, and I'd like to acknowledge my co-authors, Peter Nielsen and Paulina Bittner. This is also about the Wake Island hydroacoustic station, and it turns out that this is on the migration path of fin whales. Fin whales are some of the largest whales, and they emit in 15 to 50 hertz frequency band distinct signals, and when they pass over Wake Island, they sometimes for a very long time, several hours, up to a day or so, emit continuously within 30 seconds a sequence of A and B calls. So the poster will find out how we deducted that the A and B signal actually come from the same whale and not from different whales, as has been suggested by other authors. And also we extracted the source wavelet when the whale calls. Its signal is very polluted by multiple reflections. Using very simple techniques, we were able to extract the actual source directly from the whale itself. And so we were able to do that because of very good quality of the IMS data. And also we will show on the poster a very precise track that we could extract. So, so come and see the poster. This is at screen number 28. Thank you.
Wow, that was some amazing research. I think this is the best lightning talk I've seen all week. And so you're going to be very, very busy. Let's give the round of applause. I guess just in closing, please get to your posters by noon. And yes, congratulations, and hope it's an interesting session. You'll learn a lot and have a lot of customers. So yes, thank you.